Hello everyone. The previous discussions give us the idea on the effect of fluid pressure depending on its boundaries, whether it is a plane or a curved surface. In this video, let us now apply the concepts on hydrostatics to analyze structures in contact with fluids. One of the applications of hydrostatics is on the design and construction of dams. And the basic description of a dam is a structure which prevents the flow of water and accumulates it in a reservoir. Why is there a need to build a dam? Here are some of the purposes for dam construction. 1. Drinking and domestic water supply. Next is for flood control. Third is irrigation. Next is for industrial water supply. We have also for hydroelectric energy production, and next is or last is for retention and control of sediments. Dams can be identified depending on its classifications. So first classification of a dam is according to the size of the dam. So we have small dam and large dam. So the difference between the two is that International Commission on Large Dams or ICOLD assumes a dam as big when its height is bigger than 15 meters. So when the dam is lesser than 15, so obviously it is a small dam. And also, the dam is considered as large or big dam if the height of the dam is between 10 and 15 meters and matches the following criteria. Then ICOLD accepts the dam as big if the crest length is bigger than 500 meters. So anyways, the crest is the peak or top of the dam. And also, if the reservoir capacity is larger than 1 million cubic meters, then also if the flood discharge is more than 2,000 cubic meter per second, and also if there are some difficulties in the construction of foundation. Next classification of a dam is according to height of the dam. So we have for high dam or large dam, it is considered as high dam or large dam if the height of the dam is bigger than 100 meters. And also, if the height of the dam is between 50 meters and 100 meters, it is considered as medium dam. And obviously, anything lower than 50 meters is considered as low dam or small dam. The third classification of a dam is according to the statical design of dam body. Here are some of the statical design of dam body. First is we have gravity dams. Gravity dams use their triangular shape and the shear weight of the rock and concrete structure to hold back the water in the reservoir. Here in fluid mechanics, we'll be analyzing more on gravity dams. So next is the arc dams. So arc dams utilize the strength of an arc to displace the load of water behind it onto the rock walls that is built into. And last is we have the buttress dams. Buttress dams use multiple reinforced columns to support a dam that has a relatively thin structure. Because of this, these dams often use half as much concrete as gravity dams. We're done with the short introduction on the structure of the dam. Here are the basic parts of a gravity dam we needed for design calculation. First is we have the reservoir of water with high elevation head is the upstream side of or headwater, while on the other side with low elevation is the downstream side or tailwater. The bottom ends of a gravity dam are the hill, which is located on the upstream side, and on the downstream side is we have the toe. The toe is the point where the righting and overturning moment are produced. Let us now analyze dams statically whether it can safely carry external loads by following these procedures. So first is we have to consider 1 unit length or 1 meter length of dam perpendicular to the cross-section. So next is we determine all the forces acting. So for vertical forces, we have the weight of the dam. F sub V is the weight of the water in the upstream side if there's any. So sometimes we use F sub Y or F sub V. But uh, it is the vertical component of the hydrostatic pressure. Next, we have for U is the hydrostatic uplift. And it is the upward pressure exerted by water as it seeps through the body of the dam or its foundation. And also, we have the weight of permanent structures on the dam. Then, we also have, for horizontal forces, we have the horizontal component of the total hydrostatic force, and also the wind pressure, wave action, floating bodies, earthquake load, and etc. The third step is we solve for the reaction. So to solve for the horizontal reaction or horizontal component of the reaction is we take the summation of forces along the horizontal axis. So the horizontal component is equal to the summation of the horizontal forces. Next is for the vertical component of the reaction. Then we apply equilibrium equation to determine the vertical component of the reaction. So we have the vertical component is equals to the sum of all the vertical forces acting on the dam. The next step is we determine the moment about the toe. So to determine the righting moment, it is the sum of all rotations towards the upstream side. So based from the figure, so to determine the righting moment, so it is the sum of all rotations towards the upstream side. So as you can notice, it produces a counterclockwise rotation. Then for the overturning moment, it is the sum of all rotations towards the downstream side. So based from the figure, so the overturning moment is the sum of all rotations towards the downstream side. So as you can notice, it produces a clockwise rotation. So next is determine the location of the RY or the location of the vertical component of the reaction, and it is measured from the toe. So to determine it, we take moments at the toe, and the result is the distance from the toe to uh, the vertical reaction is equals to the difference between the righting moment and the overturning moment divided by Ry. And to determine whether the dam is safe or not, so we determine the factor of safety. So we have factor of safety against sliding. So to determine the factor of safety against sliding, so it is equal to the coefficient of friction between the base of the dam and the foundation multiplied by the vertical component of the reaction divided by the horizontal component of the reaction. So the result or the value of the factor of safety against sliding must not, or I mean, must be greater than 1 in order for it to be safe. And for the factor of safety against overturning, so we have, it is the ratio of the riding moment and the overturning moment. So again, it should be greater than 1 for it to be safe. Determining the dam foundation pressure is also part of the analysis of gravity dams. Here is how we can determine the magnitude of pressure intensities acting on the foundation of the dam. To determine the foundation pressure, some of the design considerations must be met. One of it is we consider the value of the eccentricity at the bottom cross-section of the dam. The value of eccentricity will give us the shape of the soil pressure profile as shown. So, eccentricity is the distance between the vertical reaction and the center of gravity at the bottom of the dam. So, we obtain it by this formula. So, the eccentricity is equals to 1/2 times the base to locate the center of gravity of the dam minus the location of the Ry relative to tau. So we have 1/2 b or b over 2 minus x bar is the eccentricity. So to determine the shape of the soil pressure diagram or soil pressure profile, so we consider these provisions. So if the eccentricity is less than or equal to b over 6, Ry is within the middle third and the foundation pressure is trapezoidal acting from heel to toe. And if E is exactly b over 6, the shape of foundation pressure is triangular, also acting from heel to toe. So b over 6 is the middle third or half of the middle third. So if the eccentricity is less than or equal to b over 6, so meaning it is within the middle third or it is inside the middle third of the base. And if the eccentricity is exactly b over 6, so it falls on this part or on the exactly b over 6, so the soil pressure profile will not be trapezoidal. Instead, it is a triangular shape. So here, so we take it into consideration whether if eccentricity is less than or equal to b over 6. But how about if the eccentricity is greater than b over 6 or it falls outside the middle third? So this will be the formula. So if the eccentricity is less than or equal to b over 6, the location of Ry falls inside the middle third. So if that's the case, the shape of the soil pressure diagram is trapezoidal. And if the eccentricity is exactly b over 6, the shape of soil pressure diagram is triangular, measured from heel to toe. So, again, if the Ry falls inside the middle third, the formula for the foundation pressure is equal to negative Ry over b times 1 plus or minus 6e over b, which is derived from the formula for the combined stress. For the sign of 6e over b, use positive sign at point where Ry is nearest. So as you can notice, Ry is near the toe, so we use positive sign. And use negative sign for the foundation pressure at the heel. A negative pressure intensity indicates compressive stress, and a positive Q indicates tensile stress. So, a positive Q will occur when the eccentricity is greater than b over 6. So, in foundation design, soil is not allowed to carry tensile stress. Thus, any positive tensile stress will be neglected in the analysis. So if the eccentricity is greater than b over 6, so Ry is outside the middle third, and the foundation pressure is triangular. And to determine the formula for, the foundation pressure is equals to 2Ry over 3 times x bar.